Howdy everyone. Today on this here lovely Saturday evening, we have another fun-filled adventure with applied strength of materials. So today we're going to be taking a look at this example here, which is from an assignment that is due in a few days. So we're going to be going through this question here. Fair warning, because of the intricacies and the nuances involved with this sort of question, there could be some things that are missed. However, the methodology is really what you need to digest because um, most of these questions, in fact, these questions in general are not about the answer, but the method that you follow to get to that answer. And so, again, we really want to just pay attention to the thought process involved with these questions and use that to take us along until we get to our desired answer. With that being said, let's let's take a look at. Let's actually read this question here. So a propped cantilever is supported and loaded as shown in Figure 1 below. Two similar steel sections welded together, each with a second moment area of 480 times 10 to the negative 6 meters to the fourth, with Young's modulus value of 210 gigapascals and Poisson's ratio is 0.32. First things first, Poisson's ratio. We do not care about that. We do not use it in this question. It's only there as additional information, but for this particular set of questioning, we will not be using it. All right? And in fact, it's there as a way to throw people off, because if you don't understand this and you see it there, you see a number, you see something that you can use, you're going to find some way to use it, right? And that's not what we need to do. We need to be smart people and understand what it is we're doing. Okay, so question A um, asks us to find the reaction and moment at A, and we take our reference from the left side onwards. And so to do anything, to answer any question, we first have to establish our bending moment equation, right? So we can see, we take a look here at our diagram. We can see this cantilever, which is propped up by the support at B, and it's got an overhang that reaches up until C with some UDLs. It may look complicated, but it's actually not. Just stick to what you know, and you'll be fine. So if we start from here and move towards the right, then we can write our bending moment equation, which starts off on this side as EI d squared y over e squared x, right? That's going to be equal to what do we have, whatever we have here, right? So it's, so hold on, how about I do this? How about I first, let me first draw this. I want to pause this because it's going to take too much. Alright, so I just had to draw that for us real quick. So let's carry on. So we've established that here we've got RA and we've also got MA. Now we assume that MA works in an anti-clockwise direction because we've got two UDLs here that will act in a clockwise direction. So if we take all clockwise moments to be positive and all anti-clockwise moments to be negative, then RA RA will be considered to be a positive moment, because if you're standing at some arbitrary point X and look to the left, then you're going to have this moment traveling clockwise in relation to X. So RA is positive, and it is multiplied by X to the first power. Then you've got MA, which we said is anti-clockwise, so it's negative. So you subtract MA, and it too is multiplied by X, but because it's already a bending moment, you raise its exponent to 0. Then you've got this here. If you know how to construct its bending moment, then you will know that it will be plus 48 over 2 plus, no, it's negative, my bad. Yeah, it's negative. And when we consider UDLs that are offset from the reference point, then we extend it all the way to, we treat it as if it is a UDL that's all the way up to the arbitrary reference arbitrary point, and then we compensate for that by subtracting that added distance. This is because we want all of our distances to be in reference to X. So we'll have here X minus this distance here being 1, and so X minus 1 would give you the rest of this space here, which we are treating as our actual UDL, but it's not. And because it's not, this is raised to the 2. Because it's not, we have to compensate it by removing this added distance, right? So it's going to be 48 again, because it's the same UDL, it's the same weight distribution. Divide by 2, and now it's X minus this distance here, because this is the only distance that UDL covers. So it's X minus 3 meters, minus 3 raised to the second power. Then we move on to this point here, RB. RB here is clockwise, so it's positive. So this compensation would basically act down here to counteract that what should we call that? Basically the fake portion of the UDL. Okay, it's now RB. It needs to be multiplied by X minus 4. So X minus 4, and it is only to the first power. Then we come here to our final UDL, which acts anti-clockwise, so it's minus 24, right, divided by 2, and here it does not need to be compensated because it's already on the reference. So it's just X minus the distance, this distance here. So that's 1, 3, 4, 5 minus 5. And remember, it's squared. So if I'm to explain this quickly, how this works, it's basically, if you've got a UDL, right, you want to convert it to a point load, and you also need to consider where that point load acts. So to convert the UDL to a point load, we're multiplying its weight distribution by the length that it occupies, and that you need to multiply by the distance at its half point to your reference. So it would be half of its length multiplied by 2 plus whatever distance it would be to your reference. In this case, it doesn't. There is no difference because it's sitting on the reference. If it was this one here, it would be halfway. I think that would be about somewhere here. It would be halfway there. Okay, let me not confuse anyone. Alright, let's just carry on. Alright. Cool, so we've got our bending moment equation. Now we need to use our double integration method to find the equation of the slope and the equation of the deflection. So if we integrate this once, we're going to have e I dy over dx, which is going to be equal to, if you integrate that, so over 2x squared. If you integrate this, it just becomes x to the first power, to the power of 1. Then this one here, that will integrate to 3, and you multiply by the denominator, it's going to give you 6 x minus 1 to the 3 plus 48 over 2. My bad. But okay, I'm just going to complete this whole thing for the sake of time. Alright, so this is the completed version. 48 over 6 times x minus 3 to the third. Then you've got rb over 2 multiplied by x to the minus 4 squared, all the way to this one here, and you add your constant of integration. So let's do now the second integration, which will give us e I times y. This is for the deflection now, and we just integrate as we did before. This time it's going to equal 6, because that integrates to 3 and you multiply by the denominator. And I'm going to do that for the rest of them, so I'll just pause again. Alright, so integrating again, It's the same process, and here you're going to get another constant of integration, and the last one is going to now be integrated to have an x value. So here we've got our bending moment, our slope, and deflection equation. So we can move on to the next part, which is defining what these values are. We need to find what these constants of integration are, and to do that we use our boundary conditions. Now in this case we have three boundary conditions that we can take a look at. That is the slope of the system when x is 0 at the cantilever, it'll be 0, and the deflection at 0 will also be 0. Then the deflection at x equal to 4, which is at the point B, will be 0, but not the slope, only the deflection. Right? Okay. So let's input the first boundary condition, that being y is equal to 0 at x is equal to 0. So we know that if we input 0 anywhere here, the answer will be 0. So y here is 0, that's 0, that's 0. Now here it's not 0, but it is negative, and by Macaulay's method we know that any negative parameter should be discarded. Same here, same there, same there. This will just equate to 0 because you're multiplying a by 0, which means that b is equal to 0. Then your second boundary condition, which is the deflection being 0 at x equals 0, will yield the exact same thing for a. Why? If you take a look at this equation here, you substitute 0 there, substitute 0 there, there. If you substitute 0 there, it gets discarded because it's negative. There, and there. And so a must be equal to 0. Then for our last boundary condition now, which is at point B, y is equal to 0 at x equal to, let's just confirm the distance, so 4 meters. Alright, so we can substitute that into our equation. So RA over, this is 6, RA over 6 divided by 4, and that's to the third power minus MA over 2 times 4 squared. Yeah, so I'm just going to input everything here. Cool. So inputting 4 into this expression here, we get 48 over 24 times x minus 1, which is 3. Then for this one, it's equal to 1. Then here it's 4 minus 4, which is equal to 0. 4 minus 5, which is equal to negative 5. And we know that a and b are 0, so they don't even get included. Now this being 0 and that being negative immediately just gets discarded, so it does not get considered. Now if we simplify this, we're going to have 32 over 3 RA minus 8 MA. Okay, and subtracted by 162 plus 2, and that all equals to 0. And so if we rearrange that, it's 32 over 3 minus 8 MA, which is equal to positive 160. Cool. So this can be labeled equation 3 because we call this equation 1 and that equation 2. We'll call this equation 3. Right. So now we have two unknowns here, because this is an indeterminate beam, right? Indeterminate beams have more unknowns than there are equations available to evaluate. So what we have to do is find some complementary equations from our system that can help us evaluate all of the unknowns. And what we use for that are the static equilibrium equations around specific points. Now we've got 2 points here that we can evaluate, that being A and B. So we need to ask ourselves, what would be the most useful point to evaluate the static equilibrium equation around? And that would be, in this case, if you think about it logically, it would be point B, because we have two unknowns here, RA and MA, right? And so if we evaluate the bending moments about B, then we'll have RA appear again and MA appear again, and we won't have to deal with RB, which in this case does not contribute to the bending moments as it is at this point. So then we take the sum of moments about B, which for the system to be in equilibrium must be 0. So in effect, this acts as an additional boundary condition for our system, which then allows us to evaluate what those unknowns are. So what are the bending moments around here? We've got MA, which is anti-clockwise, so it's going to be negative, minus MA. We've got RA multiplied by its distance to B, which will produce a clockwise moment, and that distance is 4 meters. So plus RA multiplied by 4. That's a terrible 4. Okay. Yeah. So then we multiply that by we add the UDL here. There's 48 kilonewtons per meter. Now, unlike the bending moment equation, we do not need to compensate this here. We can just take it as we usually do with bending moments about a point, and that is multiply it by the length that it covers, and take the distance from the reference point to its center, what I was mentioning earlier, right? So in this case, we'll have 48 times 2 times what's the distance it covers, 1 plus the halfway here would be 1, so that's 2. Then on the other side here, same with this 24 kilonewton UDL, wait, actually, let's just confirm this is clockwise, so it's positive. It is positive. 24 by 2, and the distance should also be 2. Yeah, by another 2, and that all equals to 0. Yeah. 3. Now let's evaluate this. Let's simplify it. So we'll have 4RA here minus MA, and if we take both of these to the other side, them being numbers, actually I calculated this already, let me not even do that again. So it's going to give me 96, and this is equation 4. Right, now for us to solve these two equations simultaneously, which will give us our unknowns, it's useful to just scale this up by one of these, to scale to scale this one up to this specific number here, because they will just then cancel out when you subtract them, right? So if we multiply everything here by 8, and we're going to have 4 by 8, which is 32 RA minus 8 MA, that equals to 96 by 8 is 768, and we can call this 4 prime. I don't know why I drew that on there. 4 prime. Now let's subtract equation 3 from 4 prime. That's going to be 32 MA minus 8 MA, which is equal to 768 minus 32 over 2. Did I just draw MA twice? My word. It is now 22:11. I'm tired. RA, cool. Minus 8 MA, which is equal to 160. Alright, let's evaluate that. It will give us 64 RA equals to 608, which therefore means RA is equal to 28.5 kilonewtons. Lovely. Now we can then evaluate what our bending moment at A is by substituting RA back into equation 4. So it'll be 4 RA minus 96, which is equal to 4 times 28.5 minus 96, and that is equal to 18 kilonewton meters. Yeah, now we've got our reaction at A, and we've got our bending moment at A. The only thing missing now is our reaction at B, and we can use the exact same method we just did to find the last two unknowns, and that is evaluate the static equilibrium at a point. So we've exhausted this one. The only one we have left is A. Let's do that again. So the sum of moments about A is equal to 0. Must be for the system to be in equilibrium. So we know that MA is negative. We know that this is going to produce a clockwise moment, so it's going to be positive. So that's plus 48 by 2 by, what's the distance this time? 1 plus halfway here would be 1, so it's 2 again. And note that RA does not produce a bending moment because it's at A. Then B, RB is at 4 meters from the point A, and it produces an anti-clockwise bending moment, so it's actually meant to be negative. RB multiplied by 4. And so the only thing we have left is this 24 kilonewton per meter UDL, and that it acts at 1, 3, 4, 5 halfway there, and that is 6 meters from A. So 24 multiplied by its length multiplied by its distance from the reference, that must equal to 0. And so RB, or 4RB, is equal to what is that simplified? 192 minus 288 plus 288 minus 18. That's going to give us 462, which therefore means RB is equal to 115.5 kilonewtons. Sweet. Now to test it out, we know that the forces going up need to equal the forces going down. That's how we know the system is in fact in equilibrium, and we in fact derived the correct reactions. So RA plus RB needs to equal to what is this, 48, right? Yeah, 48 by 2 plus 24 by 2. That is RA plus RB. It's RA is 28.5 plus 115.5, which is equal to 144. And these two are in fact equal to 144, so they are equal. Now, doing that, we will have answered the first two questions here, the reaction and moment at A, and the reaction and at the prop B. Now, go on to B. We need to solve the slope in degrees, 1 meter from the support, and the deflection at the free end point C. How long is this video been going on? 30 minutes. I need to teach faster. Okay, so B now. So this part's relatively simple. All we're doing is substituting into now our slope equation, which I'm just going to copy because ain't nobody got time for that. Alright, let's just copy that. Sweet. And we already know that A is 0, so we don't need it here. Now, if we just rearrange that, your x at x equals to 1, it's going to be, so we write here 10 to the power 3 because that converts it to meters for us, It's just something you see in the text, so just stick to that. Then at the bottom here we have EI, because we divided entire um, the entire equation by that, and E is equal to 210 gigapascals. And I, if you remember, we have two steel sections welded together with the second moment of area of 480. So it means that the entire second moment of area is twice that of those individual steel beams. So we must multiply this by 2. 2 times 480 times 10 to the minus 6. Okay, and we've got to open this bracket here to substitute what we need to. So 28.5 over 2 multiplied by 1 squared minus MA, which is 18 times 1. So here, if we substitute 1, it's going to be 0, so it gets discarded. This will be negative, gets discarded. That will be negative, gets discarded. That's negative, gets discarded. Cool. So we only have those two things. Simplified. 10 to the 3. Let me be smart. Cool. So that's going to yield minus 3.75. Yeah, so again, this is all under the assumption that my calculations are correct, but the method is quite fine. So that'll yield minus 18.6 times 10 to the minus 6, and that's radians. Okay, and we must convert it now to degrees, and you should know that to convert radians to degrees is just multiplied by 108 over pi. That's going to give negative 0.001 degrees. So that is the slope at 1 meter away from A. And then the last question is the deflection at the free end point C. So that is the entirety of this length here, 1, 3, 4, 5, 7 meters. Okay, so do the same thing we just did now. Let's copy that. Cool. I don't need this. Alright, so y at 7 meters is equal to the same 10 to the 3 over yeah, and so put things in here now. 28.5 over 6 7 cubed minus 18 over 2 divided by 7 squared. This one's going to be a bit long. 48 24 minus 6. Right, because it's 7 minus 1 to the 4th power plus 48 over 24 multiplied by 4. 7 minus 3 is 4 to the 4th power plus RP, which we found to be 115.5 newtons over 6 multiplied by 3 to the 3rd minus 2 to the 4th. Alright, simplify that. We are smart engineers here. We don't waste time. Cool. Now, yeah. 1629.4 minus 441 minus 2592 plus 512. Looks like an R. Yeah. That's 519.75 minus 16. Okay. Further simplifying that. Will give us 388, right? And that's going to yield minus 1924.6 times 10 to the minus 6 meters. That is the same as minus 1.925 millimeters. Alright. Yeah, so it's quite a large deflection if you think about it. But I think it's reasonable because we have here a cantilever, right? So at the far end without a support, the deflection is bound to be higher than if it was a simply supported beam, or what do you call it when both sides are attached to a wall? Yeah, whatever that thing is. But yeah, that's effectively all there is to it. Yeah, again, I might have made a mistake on a calculation somewhere. I don't know. Particularly in these last two questions, it's possible. You guys can let me know if that's the case. But yeah, that's all there is to the method that you actually have to know to solve this.